All right. So we're on chapter 8 of the Hamel book. So this chapter was all about dimensionality reduction. So I'll start by just touching on some of the key points from this chapter. So we talk about the curse of dimensionality, we talk about projection, we talk about manifold learning and PCA, random projection, and LLE. I see a request for the document in the chat. Let me drop that for everyone. So there's the docs. Um, so yeah, those are the major concepts of this chapter. To start, I'll talk a little bit about the curse of dimensionality and why we want to reduce our dimensions at all. So, um, the first thing that I would put in your mind is like when you're thinking about dimensions, you might have like number lines and then 3D and then 4D and all these other things that you can't visualize. The way that I think about it in terms of like machine learning terms is the number of features. So in previous weeks, we've looked at like the iris data set where they're looking at the width and the length of the petals. So you have two dimensions basically. And then say you have a third where you're saying measure the height of the plant or something like that. So every feature is potentially a new dimension. And so when you're thinking of dimensions, I typically think of features, at least in this context. So it can be your input features, but it can also be your output dimension as well if you're predicting three things or four things or five things or something like that. So talking about the curse of dimensionality for a second, we as humans have strong intuition of like 1D, 2D, 3D. We learn these things in school and you understand like a 3D object. I can rotate it, I can translate it, I can do certain things like that. And we also have some intuition of distance. So like the back of the room is so far away. But when we start going 4, 5, 6, etc., much higher dimensions, that notion kind of changes, and we don't have as good of intuition of that. So one of the things that I wanted to stress on is that as you add more dimensions, your points become further and further apart on average. So if you have 100 dimensions, then your points are going to be further apart than if you only have 3 dimensions, if you're just randomly sampling in the space. Um, and the other thing is when you have more dimensions, it's more likely that one of them is going to land on sort of an extreme value. So if you say, I have 100 dimensions and I'm just randomly sampling within all of them, it's very likely that one of them is going to end up on some sort of extreme value out of that set of 100. Um, so one of the things in terms of like training models is ideally we want good coverage of our data. So if you have a range of different possible uh, leaf lengths and leaf widths and plant height, you want good coverage showing like here are all of the possible values that it might be. Um, so one of the things that I did was I took Claude and I just had it kind of show this concept a little bit. So in 1D, if we want to have all of these points spaced out 0.1 distance from each other, you end up with this simple number line where you're saying 0.1, 0.1, 0.1. If you extend that to 2D, then you have this cube. And instead of needing 21 points to fill up the space, you need 441 because now you're saying this many points in one direction, this many points in the other direction. And then if you extend that to 3D, then you all of a sudden have 9,261 points. So it just scales extremely rapidly. If you want uniform coverage of the entire set of features, then going past even 10 dimensions, you have 10 features, it's impossible to get very uniform coverage of this space. So this is just extrapolating this all the way out to 10. So if we wanted good coverage in a 10 dimensional space, we would need 16.68 trillion points. So it's very common for us to have problems where we have even larger than 10 dimensions, and you can't possibly cover that amount. You don't have 16.68 trillion data points to fill out that space. So here's a couple extra plots that I showed to also show the extreme values. So as we extend more dimensions, we're more likely to get something that's towards the boundary. So if we are, say our space is from -1 to 1, and then we're randomly sampling from it, by the time we have 100 dimensions, it's almost guaranteed we have something very close to the boundary. So it really changes our perception of like we think of 3D and then everything's kind of uniform and normally distributed, but when we go to more and more dimensions, you end up with random things that are at extreme values. And then this plot on the right is also showing the distance between points, the distance between the closest point. So several important things here. So in this plot, it's showing if we want uniform coverage of the entire feature space, then you need this many points. But in reality, typically, you don't actually need full coverage of all possibilities at all because your data probably only falls in some subset of that space. You probably don't actually see every single possible combination out in the wild. Like if this is saying like height and width and length of petals, you probably don't have a 10-foot tall plant that has tiny little baby leaves. So there's probably a large portion of this 3D space or more that you don't even really need to cover. So that was just on the cursive dimensionality. I can pause any questions there to start. Okay.
My question is, why would the extreme values be any different in interpretation from any other point? What is the significance?
So the idea here is basically in 2D space, you're looking at two different features, and if you're just saying they're random, some of them are going to end up 0.5, some of them are going to end up 0.9, something like that. As you're adding more and more dimensions, you're sampling from more of those features. And so it's likely that one of your values is going to end up at one of the boundaries. So let's say you have 100 and you're sampling from each one of those. One of them is going to end up probably really high. One of them is probably going to end up really low. But you don't have that phenomenon when you only have 3 dimensions because it's probably pretty likely that they end up more in the middle because you're not taking 100 chances at an extreme value.
Thank you.
Yeah.
If I could add on to that really briefly, we're not saying that the odds are the data point will wind up in a corner where it's extreme in all of the dimensions. We're saying just for it to be near a side, a face, whatever, of the hypercube, it only has to be really extreme in one of all of the different dimensions. And so you can see that, like, if you're just rolling random number generator, in order to get the odds of getting one really high or really low value, the more times you roll, the better the chance. So in 3D, you only have 3 chances to roll something, let's say, that's greater than 0.95 or less than 0.05. You go 100 dimensions, and then it's like, yeah, it's pretty likely that you'll get one of those. And so that means it's near the exterior, near the face. But in case it was untrue, we're not saying that they're all crammed in the corner, because that actually becomes less likely, because then you'd have to be extreme in 100 different things. So in that sense, yeah.
Is it useful to think of it kind of like a sparse array versus a dense array?
It depends on the context. So like what I'm showing in this one is you have the dense points throughout all of space. But in reality, you typically have much more sparsity than that. So you have not many of the coordinates are actually taken care of. They're not covered.
So was it like it's a range of possible values, and then the data set fills in, they're like all little buckets, and then the from the data set it will fill those buckets?
Um, So you can, what I've shown on this graph is like uniform, just like full coverage. But when you typically have data, your data isn't going to have full coverage of that. So it's just going to be in small pockets of the space. So I wouldn't necessarily represent it as a sparse array, but it is going to be sparse within the space. Like you're not going to have full coverage like this.
Thank you.
Yeah.
Yeah, and if I could add on to that, so like if you just think about people, okay, let's say you measured height, weight, I don't know, whatever, like what your arm wingspan is, the distance between your thumb and your pinky or whatever, right? Like you may say the tallest person, let's say, is I don't even know what, 7'6", and the shortest person is 3 feet or whatever. Okay. And then let's say the lightest person, I don't know, adult, whatever, is 50 pounds, and the heaviest person is 500 pounds. You're probably never going to have a 7 foot tall, 50-pound person. So when we talk about sparse matrices or whatever, usually we're talking about zeros. And so we're not saying that somebody will have a 0 weight or a 0 wingspan or a 0 waist size. But you can just imagine if you had all of these different measurements, you're not going to find 800-pound people with 25-inch waists. It's just unlikely, right? In the real world, you can have nulls because of measurement error or the person forgot to record it. But in terms of like the actual data, what we're saying is that if there's a whole range of values, you don't see every single combination of weight and height, every single combination of weight, height, and waist size. There's actually only for a given weight, there's only a smaller range of heights that appear in real life. And there's only a smaller range of whatever, wingspans. There aren't any 3 feet tall people who have 6.5 foot wingspans, right? So that's just, that's like one example that I made up, but just so for any problem that you're doing, even, the pixel values of cats and dogs or whatever, there's just certain things that are extremely unlikely. You're not going to have a picture of a dog where one pixel is completely dark black, the adjacent pixel is completely white, the adjacent pixel is completely red, and keep going like that, right? You tend to have this thing where in the middle of the body, all of the pixels are close in color. And then eventually, you'll get a brown part or black part or whatever, right? So it's just out of all of these different possible combos of values, we don't really need to worry about what Ryan was saying, full coverage. Does that help?
So I'm not quite sure how to phrase this question, but in the example of the petals and the flowers, can you give an example of where you might have an extreme value that would come up when you have too many dimensions, like what the dimensions might be to create that extreme value that wouldn't show up in a lower dimensionality? Does that make sense?
Yeah. So in that example, you probably don't have extreme values, but that's kind of going to the point that Ted was talking about, where it's like we actually have this potential range that can be massive, but in reality, your data probably operates in some smaller region of that. So like on plants, we know there's certain bounds on each of the different measurements. So you might have some outlier plant that is actually very tall but has tiny leaves or something like that. It is possible for that to happen, but in reality, you probably have bigger plants and smaller plants, and they probably have corresponding leaf size.
No, I understand that part of it. My question is, I assume these extreme values you're talking about are misleading. So you don't want those things to show up in your data, because they may show properties that don't exist because of the higher dimensionality. Can you think of an example offhand where this would occur? Is it in combining things, like saying, this dimension is kettle length versus color versus, and combine all the things? I mean, what would produce something like this?
So one of the first things you were saying, I wouldn't necessarily say that it's a problem to have these extreme values. That might actually be the defining characteristic of some feature. It might be the most useful thing to tell some plant versus some other kind of plant. Say, oh, this one has very wide and very short leaves, for example. So it's not necessarily saying that the extreme values are bad. It's just for what we're talking about with the dimensionality is like the space can be so wide when you have so many dimensions, and it's possible for you to have very extreme values when you have high dimensions. In reality, when you look at real data, you probably don't actually have that phenomenon.
If I could take a stab at answering that question, I'm going to answer it not the way you asked, though. Okay. Which is that if you had 100 features like Ryan's talking about, okay, and let's say it's all just this plant. So you've measured height and the widths and whatever of the petals and the glossiness of the leaves and whatever, okay. So your question is, can you give me an example? And that's one of the points of this chapter, is that real world phenomenon tends not to have those kinds of extreme values. Or if you had one plant that's like really tall, then it's probably really big in other ways as well, or whatever. Okay. But if you just built 100-dimensional linear regression, if I were to anthropomorphize a little bit, the model doesn't know this is a real world problem, and it thinks it wants to make accurate predictions over the entire 100-dimensional space and make good predictions on all the edges and all the corners and all the everything. And your intuition from smaller numbers of dimensions, like say 2 dimensions, if I said, well, imagine a square, but you really only need to make predictions on the circle that's inscribed inside the square, you'd be like, it's kind of the same thing whether I make predictions for the circle, I make predictions for the whole square, right? Because it's just like 4 little corners. What difference does it make? But in 100 dimensions, there's a massive difference between the small subset that plants actually occupy and trying to fill all edges and corners of this 100-dimensional hypercube. And so that contrast between the two, you're actually asking the perfect question, because by us saying no, we actually have a hard time coming up with an example of something with extreme values. That's why we're saying in this chapter we might be able to do something to make the problem smaller, because we don't actually have to worry about those extreme values in real life, right? There may be one corner where like the really tall plant also has really thick stems and really large, it's just large in lots of ways, right? It's just big. And there might be a really small plant that's really small lots of ways, but you're just not going to fill up all, whatever the heck it is, 2 to the 100th corners of this possible measurement space. And so if everything lives on close, in the extreme, imagine everything just lives close to one line where either, everything that's twice as big is twice as big in every measurement, in height and width, in whatever, then you really don't need 100-dimensional thing. You really only need one thing, which says how big is the plant, and then when it's big, every single number is big, and when it's small, every single number is small.
One last question: is this related to overdetermination?
Yeah, that's kind of what we're getting at. In this case, though, we will generalize, okay, because in my overly simplistic example of the plants, where if you know one dimension is large, everything is large, there might be a little bit more variety than that. Okay. So if you think cats and dogs and like the shape of the face, there's not just like one measurement you could do that says, oh, as soon as I know this, I know it's a dog. As soon as I see that, I know it's a cat. But it's probably a handful, like 3 things. If you knew like how long the snout is, then you probably like 75% sure if it's long, it's a dog. And then maybe there's a few exceptions, like a bulldog, but like, so maybe you can imagine that you've got all these measurements, or if you take a picture, you've got all these pixels, but if you boiled it down to about 3 ratios, you might be able to have a pretty good predictor, dog versus cat. Okay. So it's not that there's like a more literal overdetermined and then so ultimately what we're going to talk about is this idea of a lower dimensional manifold. Okay. but it's not necessarily just like a line. It might have different branches, you know, the bulldog branch versus the 85% of dogs have sort of that canonical longer snout or whatever. That help? Could you pass the mic?
So is it possible to, is there something built in to where it will look and say, hey, you have like 100 features, but your data set is like there's like a lot of like dead space, or maybe like you run a regret, like a linear regression for each like feature, and then it says like, you know what, actually you could maybe decrease your features, or is that something that you would write yourself in like Python or something?
Yeah, so that's kind of the idea that we're building into is like you probably have all of these features and a lot of them probably don't have useful information or they don't have very much variation. So that's the ideas that we're building towards is like how do you reduce that down to something that's more information dense so that it doesn't have all this dead space where there's no uh data points, there's no coverage, there's no information there. Yeah, so that's part of what we're building into. So there's scikit-learn stuff that directly will do that for you, basically saying we have 100 dimensions, let's reduce it down to 20 because I know most of these don't cover very much of the space, they're not very spread out, they don't have useful information. So you can do that in various different ways, and that's what we're looking at today.
Just one more question. Is there anything that's similar to like in web development, you have unit testing? Is there anything that's like similar in terms of the data, or not really?
So in this context specifically, one of the things that you can do is you can check how much of your variation you're keeping. So like if you want to test and say, make sure I'm not throwing away too much information, for example, that's one way that you can have a test automatically saying, make sure I'm keeping 90%, 95% of my variance or something like that. So you can have something a little bit automated. So a new problem, you can still make sure, okay, I'm reducing my dimensions, but I'm not throwing away too much of the data. Does that answer?
Yeah, thank you.
Yeah. So moving on, these are all great segues into the next topic, which is projection. So we have this is an example of some 3D data. So it has X1, X2, X3 measurements. That's all of these red points. And then what projection is saying is basically we can put a plane somewhere in there, and then we can project onto it. And so in that way, we're reducing from a 3D space into a 2D space. And we can do this to any reduction that we want. We could crush this down to 1D. We could, if we had more dimensions, we could go from 100 dimensions down to 20, for example. So thinking about projection, the simple way is like imagine you have your projector and you're taking your points and then you're shooting it onto a wall, basically. So that's the simple way of looking at this. So you have points that could have been aligned like in 3D space somewhere, and then you shoot light at it, and then it's just hitting the wall, and then you just have the flat visual of it again. So imagine this is the 3D representation, and they're showing it's getting projected onto this 2D sheet of paper, basically. And then this is what it looks like when you crush it down to 2 dimensions. So this is saying we have this axis and we have this axis. And so that corresponds to this sort of 3D sheet of paper that we're looking at. Yeah, go ahead.
I know it's that's kind of oversimplified, but what the projection, would it be orthogonal to the plane, or would it be orthogonal to the surface?
It's orthogonal to this subplane that we're defining. So it's orthogonal to the piece of paper that we're sitting there. So we're basically saying shine the light where it lands on that piece of paper, basically. And it's more complicated when you start going to 100 dimensions. We don't have a clean sheet of paper anymore, but yeah, it's orthogonal. It's trying to find the shortest distance to that subplane that you're defining. So that was projection, and then the other one that we'll be looking at throughout this chapter is manifold learning. So this is a classic example. It's called the Swiss roll. And so it's this data that's wrapped up like this. And so you can see it's 3D data again. But if we tried to do that same projection step, we say crush this down into 2 dimensions, put it on our piece of paper, you can see that because it's rolled up like this, you flatten it, and you end up with these points on top of these other points, and we lost a whole bunch of information. And if you try to do this with any plane inside of it, you're still going to get that like crushed, high loss of information view of it. So the other option is to do some sort of manifold. So this is basically saying, instead of having a flat sheet of paper, find some like squiggle within space and then say, okay, project it onto that manifold. And so with that method, you can get this nice unrolling of the space in some way. So manifolds are a bit more complicated, but if you know that your data is arranged in a certain way, you might be able to reduce its dimensionality in a much better way than just trying to do PCA.
Hey, can I just make a really quick comment? So on the left there, where you see the brown kind of got overlapped with some of the orange or whatever, you could still train a model on that and it might work. So you wouldn't know that you did something suboptimal. So that's the thing, is like, we can visualize this because it's just a small 3D example. But when you're solving your actual problem, even if it's only like 8-dimensional, you still just have no way of knowing if you did a good job or not. So we'll study examples in this chapter of low dimensional things so that you have an intuition, but you won't really know. You just have to actually test to see how well things learn. And so you might use one of the techniques in this chapter and find that your model has horrible performance. And that means don't reduce the dimensionality. That technique just did not work for
you. Yeah. So there's these 2 different options, and you don't want to say, oh, manifold is always better, because that's not necessarily the case. You can definitely get something that goes awry. So they showed this sort of counter example to this. So they're doing the same Swiss roll, but instead of saying like our points are following along this and the lower values are here and the higher values are at the other side of the swirl, it's saying, what if we split it like this, and then we go do the manifold process to it again. If you did PCA, it would actually split these very cleanly, and you just get a clean line that goes through all of these. If you did manifold again, and you said that the boundary is here, then it's going to unroll it, but then it's going to make it much more complicated to draw a line through your positive and negative class. So you can see, like, you do this unrolling process, and maybe it's actually not useful for what you're trying to do. So this is one of those things where you can visualize it and get some intuition about what's going on, but in the end, you really need to like run whatever machine learning algorithm, your decision tree or your gradient boosting or your linear regression, on top of this, and try the different options and say, oh, this one's actually throwing away a lot more information than I realized, even if it gives you a pretty plot or something like that. So you have to be careful. These tricks are often used for visualization, and then they can cause other implications when you actually train models.
So in that one, the one in the lowest corner, you're saying there is no way you can do any model on that, or something is possible, or what really?
So you can train a model to extract this darker green out. It's still possible, but it makes it more complicated than it would be. Like, if in this 3D representation, you can say, if you just hit this certain X1 value, you've solved the whole problem. Whereas in this one, you're saying, I changed my dimensions, I did this fancy manifold thing, and then you go and you try and model it, and it's much more complicated than it actually
Some kind of a
is.
polynomial, like a RBF kernel or something. And
Yeah, but you can do something to solve this, absolutely, but you've overcomplicated your
Yeah.
problem for yourself. Like you had something that was simple and then you made it complicated, and then you have to use a complicated method to go solve it again. Whereas if you left it in the original data, it would have been simple. Yeah.
So it just occurs to me, and I'm sure there's a way to do this, but even for a three-dimensional plane bisecting, you have an infinite number of planes that you can put into it. And for manifolds, it would even be even more complex. So as a data scientist or a machine learning person, how do you go through the different spectrum of choices and actually get an answer?
Yeah. So that is perfect segue to PCA. So that's the next section. So this is the whole idea of, can we automatically find where to set that plane in order to maintain as much information as possible? So principal component analysis is basically, you find what's called principal components, and what you're trying to do is you're saying, basically draw these planes in exactly the right place so that you get as much variation as possible. So like here's a simple 2D example, and this is showing various different ways, exactly to what you were saying. You can align this in various different ways, and it's going to preserve or destroy different amounts of information. And so PCA is this automatic way of saying, find the subplane that gives us the most information. So like this top one is saying, let's look at the variation along this axis. We keep a lot of the information. So we've reduced it down to one dimension and we've kept a lot of the information. Whereas if we go to this more diagonal, then you end up losing quite a bit more information. And if you do this other one that's orthogonal, then you end up losing all of the information because it's taking all of this sideways variation and just crushing it down, so you just get this tiny amount of points here. So that's the idea behind PCA. Is basically, it's difficult for us to just kind of eyeball it, so there's automatic methods to go look at it and say what's the correct plane to just keep as much information as possible. So that's not necessarily saying it's going to give you the best representation to train against or to visualize or anything. It's just saying maintain as much variation, which is typically useful because you're saying put it in lower dimensions, but try and keep as much information as possible. So as long as you're not throwing away a lot of information, then it's probably still a useful representation. Yeah, go ahead.
Can you scroll up to the so in the first row, I guess it almost seems like we're unwrapping it, but then in the second row it seems like we're kind of slicing it and like almost like set like layers of sediment or something. And I'm trying to like translate this 3D to 2D space.
So in both of these, it's actually trying to do that unrolling step. It's just that we've colored the points differently. These are the same shapes that have been colored different ways, saying, okay, all of your positives are on this side, all of your negatives are on that side, or they're on different sides of this x1 value, for example. So both of these are actually unrolling, but the coloring on the right ends up different because they've been colored differently. So this one, as you're going around the loop, some of them are the lighter green, some of them are the darker green. So you reach a certain region where like this inner loop is this darker green here, and then you go around the loop more, and this outer green is what we see over here. So that's the unrolling process is still happening on this one.
Well, in the second row, it seems like there's another grid, like another plane. So, but then in the first row, I don't see it.
So in the first one, there's no grid, but you could draw something on X2 that basically says chop this in half. On this one, they're showing basically the decision boundary in order to separate your positives from your negatives is very simple. You just have to look at one variable in order to, but they're not actually using this grid in order to do anything in the unrolling process. It's just to show like, look, this is simple. We draw a little plane right here and we perfectly separated our two sets of points.
Thank you.
Yeah. So I have a little pop quiz question for the PCA stuff. I'll say the question and then I'll talk about the rest of the chapter and then we can go back at the end. So my PCA pop quiz question is basically, if we ran PCA on all of the data and then we just said keep all of the principal components, would we get the original data back or would we get something different? So basically saying if we have 100 dimensional data, we run PCA on it, and then we say keep all 100 principal components, is the data that we get back, is that going to be exactly the same or is that going to be different from the original data? So I'll go through the rest of the chapter and we'll talk about PCA and then we can go back to that if anyone wants to answer it. So to answer the previous question, we were talking about PCA is trying to find the axis that has the most variance. So like in this example, it's basically saying we find the right axis and then it gets us the most variance. And then this is only a 2D example, but if we had 3D, 4D, 5D, for example, we could have more components saying go orthogonal to the first axis and find which one preserves the most information again. And so you can do that all the way down to, if I have 5 dimensions of data, go to 5 dimensions of principal components. So SVD is a very important piece of it. I won't go into details on this. We've actually talked about it in previous chapters. Yeah, go ahead.
Are principal components always orthogonal in some sense?
Yes, yes.
Okay.
Yeah. So in my dummy example, you can say we have 100 dimensions and then we go back into 100 dimensions, or you can do subsets of that. So you can say we found 100 principal components, but only use 3 of them, for example. So you might use 2 or 3 if you're trying to visualize something. So I have this very high dimensional data, and then I want to just visualize it in a 2D plot or a 3D plot. So that's one of the applications of PCA. But then one of the other options that I see used very often is just you say like define a certain percentage of the variance that you want to keep, and then say set it to 95 or 99% or something like that. And then you can continue to use it for training or something like that, but you've greatly reduced your number of features. So say you have 1,000 features, but a lot of them are null or correlated or like not very informative. You can run PCA and say go from 1,000 features down to 100 principal components, and you see, oh, it keeps most of the variance, so I can greatly reduce my number of dimensions that I have to look on. So that's a common trick for like if people have really high dimensional data, then they might say use PCA, reduce that number, and then train a model on top of it, but try and keep as much variance as possible. So this is this plot showing the different principal components and trying to reduce it down based on various different ways. And then this is the explained variance ratio. So this is basically saying we have some high dimensional data and we want to reduce it down in certain ways. And this is showing as we take more and more principal components, we capture more and more of the variance of the data. So you could say, okay, I want to set my threshold for 90%, for example, and then it might meet at this point at like 75 or something like that. So you had 400 dimensional data, you can reduce it down to 75. If your algorithm scales poorly with number of features, then that might be very useful for you to be able to say, yeah, go ahead.
This may be way off topic, and if it is, ignore me. But I'm thinking about Fourier analysis. So if you're like, one way of doing it is saying you have sine of n and then sine of 2n and sine of 3n and sine of 4n. And in some sense, they're all considered orthogonal. And then you decompose the image or the object into, well, I guess the image into components that way. Is that the same idea as what we're doing here?
It's very related. It's very similar. It's basically saying I can reduce this down in some way that has a simpler representation. So in this, it's saying basically I have 100 features. So in our like flower example, you say height, width, whatever. And then once you do PCA on top of it, it rotates it and you can drop dimensions and stuff like that. So it's no longer in your feature space anymore. It's just some random principal components. It's similar with Fourier analysis type stuff, where you're saying I can decompose this into simpler components that represent the curve or whatever you're trying to show. It's very related. Yeah. So one of the things that they showed with PCA was that it can be used for compression. So like they showed the MNIST data set. So it has 28 by 28 pixels. And if you can do PCA on top of that, and you can reduce it down to just 10 or 15 or 20, and you keep most of the information, that's pretty interesting that you can say, go from this big pixel-wise space down to a tiny little vector of 10 principal components or something like that. So you can use it for compression, where you say I had 28 by 28, I reduce it down to 10, but I keep most of the information. So then you have a compressed representation, and you can do the inverse of that and get back your image basically in some sense. So PCA can be used for compression in that way. Two of the tricks that they mention is there's randomized PCA. So this is a different solver. So the other PCA method is basically saying, look at all of your data and try to find the exact principal components. But with randomized, you can look at subsets and be able to get approximations very quickly. And then the other thing is incremental PCA that they touched on for a little bit, which is basically if my data is so big that I can't fit the entire thing in memory at once, you can do it in little batches at a time, but it will still approach exactly the same value. So if say I have 1 billion data points and it doesn't all fit in memory, then you can do it in batches of 1 million at a time, and it will develop the principal components as it looks through the different batches of data. And so you'll get eventually the same result, but you don't have to fit the entire thing at memory. So it's useful in that regard.
So I don't know if you want to go back to your quiz question, but before we move on from PCA, I know Ryan's heard me say this before. There's one concept that I think is really important. So there's a sentence in the book where the author says, if you look at the last, in this case, it was only a three-dimensional example, whatever. But if you say the most important principal components are explaining 95% or whatever, then to paraphrase him, he's saying it's reasonable to assume that the last few principal components probably carry little information. Okay. And if I'm going to nitpick, this is an accurate statement, but what's unintuitive about this is the word probably is carrying a ton of weight in this sentence. Okay. So if I change the sentence to say it's reasonable to assume that the lower principal components carry little information, that's actually a false statement. Okay. So what we're really saying is it's low risk to assume that the lower principal components carry little information. Okay. The odds of this in a real world problem happening are relatively low, but there is absolutely no guarantee. All right. So I was trying to, I have a small example where this could happen, but I was trying to think of a clear, like silly example. So let's say you were just predicting test performance of a bunch of kids, okay? And you had something that was like a really, really good predictor, like, you know, they took an IQ test or their grades last year or something like that, right? And then you just measured hundreds of other things about the kids, their favorite foods and what clothes they wore and who's their favorite musician and their favorite athlete. It could turn out that you just have more variation in all of these other 99 directions. And so principal component's going to say like, oh, yeah, I see the maximum variation is in who is their favorite athlete. And the second most variation is in who's their favorite singer. And the third most variation is in what pizza toppings do they like. That doesn't mean that just because there's more variation that those things in any way help you predict what it is you're trying to actually model. And so it might turn out that the smallest variation is in this other thing, but that thing, which is like their grades last year, is actually the best thing for predicting what you actually want to predict. So I just want to make sure that when we use the word variation with PCA, we're talking about total variation. Ideally, we wish we had a magic wand and we could say variation that's relevant to what we're trying to predict, but we don't actually have any way of calculating that. We don't know that. And so total variation is a reasonable low risk thing to use, but just know it's not guaranteed. So it is possible that if you run PCA, your model that was so could actually devolve to being no better than random guessing. It could, in worst case, it could be that bad. You could have lost all relevant information and be left only with, who's their favorite singer, who's their favorite athlete, and that has absolutely no benefit whatsoever for what you're trying to predict.
Yeah, good point. So your principal components is trying to keep the maximum variance, but it's not trying to keep the maximum information for your specific task, which means it can totally throw away all of your predictive power if you're using this for a model after. So I'll give people a stab at this question if they want. So going back to the pop quiz question. So if you have some data and you do a PCA on top of it and you say, I had 100 dimensions going in, I'm taking 100 principal components back out, are you going to get the same data that you started with? Or are you going to get something transformed on top of it? Yeah.
I say no.
Yeah. So what I was trying to get at was basically the way that this was represented. So say you have 100 dimensions data and then you run PCA on top of it. Your first principal component is not necessarily going to be your same X1 axis or X2 axis. So you're actually going to do some rotation on top of this and you're going to pull different axes out. So you can recover 100% of your data back, but you're actually doing some rotation and then doing some unrotation to get that original data back. So you can recover all of the information, but it's not necessarily exactly the same thing that you passed in. So it's a transformation of what the data originally was.
Yeah, and in the chapter we did on trees, they said that if you run PCA and you keep everything, you haven't lost any information, but the tree might actually work a little faster because trees only do, rectangular cuts. So they can't do diagonal cuts. And so if your data was like that line you just showed, Ryan, if it was diagonal, then by orienting the line so that it's just vertical, that could help the tree learn faster.
Yeah. So you might actually have a case where you run PCA, keep all the components, and then run some linear regression or trees or something else on it, and you get better performance out of it than without doing it. It's theoretically possible. It's not necessarily likely, but it could happen. So moving on to the next section. So on random projection, so they had this section where basically they were saying with PCA, we're trying to find the highest variance axes, and then we're keeping all of the different components. One of the other options is you can actually do random projections. So you say, just grab random planes basically and project onto that. And as long as you're keeping a decent amount of dimensions, you actually keep a lot of the information. So you can be very clever and say, find the best principal components, all the different axes, or you can say, just do random, and maybe you have to do a few more dimensions, but you actually can keep a lot of the information. So that's one of those clever tricks where you can keep a lot of the information. It just might cost you a few more dimensions. So final section. So looking at the locally linear embedding. So this is basically the PCA that we were looking at. That's a linear transformation that we're doing. So this LLE is a nonlinear dimensionality reduction. So the way that I think about this is more like the kernel trick from the previous chapters, basically saying we're looking at the local neighborhoods of the different points and what they're close to, and then we're using that in order to try to unroll. So in this case, they were doing the Swiss roll again, and they're saying, look, when we do this LLE, we get this representation where it's kind of following what we want. It's not this nice flattened rectangle, but it still roughly captures what we're trying to capture in terms of the unrolling. So it's looking more at the locally related point. So if it's looking at one point and then saying what's in its neighborhood and then trying to flatten that local region versus trying to look at it more globally. So there's a whole set of different algorithms for this kind of stuff. So people use TSNE and UMAP, and they have all of these different parameters that you can tune, and they're trading off how much you're focusing on the local points and how much you're looking at the global relationships. So if we look at these points, one of the things that is broken with LLE, not broken, but it's different from the PCA approach or the other manifold learning we were looking at, is it doesn't maintain the global distances. So it's trying to keep the local distances. So this point is probably roughly the same distance to this point as it was in the higher dimensional space. But this point is probably a totally different distance from this point, for example. It's not saying at a global level, like maintain the distance relationship between all of them. Yeah, go ahead.
So basically you're overlaying like points along the dimensions, and then putting a circle or sphere or whatever around it and looking at all those nearest neighbors and then doing that somewhere else. So you're just putting a grid, I guess, effectively putting a grid across the whole thing and then looking locally at each section.
Yeah. So you're trying to look at, let me pull the Swiss roll up again. So imagine you're looking at this point and then you're saying, look at this little region around it, and then say, try and flatten that local region, versus the other approaches we're saying, look at all the other data points and all the relationships between everything else. So some of the other methods were like totally global. This one is saying focus more on individual regions and then flatten those.
But in practical terms, are you just like throwing a grid across this and then looking at local neighborhoods around the grid? Or is it more complicated than that?
It's looking at the points individually. So there's not really a grid involved. It's saying look at each point and their distance to the related points. So it's not grid in the sense that we're not like going uniformly across it. We're saying basically look at this individual point and the distances to the related points. So it's just distributed however the points are distributed.
Yeah. Have you ever seen where, like, if you just have like a 1D chart that you can try and fit like splines to say like here's a curve, fit to it, right? So in the case of like linear splines, you're just fitting line segments that approximate your curve. You may have heard of cubic splines, so then you're just using cubic functions to try and smoothly connect that. In this case of going from 3 to 2, you're just doing local pieces of paper to try and fit all the points really well. It's just harder to visualize once you get past 1D, because your piece of paper have to be everywhere, but it's still the same concept.
I guess my question is, how do you choose the points?
Yeah. So I think you were right with what you said earlier. I don't know this algorithm super well, but I think you do your nearest neighbors. I don't know if it's a ball or just a K account of your nearest neighbors. Okay. And then you fit a piece of paper to just that small set of, say, 6 points. And you do this for every set of 6 points throughout the whole thing. And then in some way you average all of those pieces of paper together, connect them into one ultimate bent piece of paper.
So every single point becomes a locus of calculation.
Yes, that's my understanding, my very limited understanding of the algorithm.
Thanks. This kind of seems similar to a map projection. Like if you take a round globe and then want to plot it into a flat piece of paper, you'd probably want cities that are neighbors to be related on them or close on the map projection. But like if you took LA and San Diego, you'd probably want them to be close when they're plotted on a flat piece of paper instead of a round globe. But I was wondering, the Swiss roll thing kind of reminded me of the Scroll Prize challenge, which you participated in. Did anybody actually use this technique for that particular challenge?
So that was part of the challenge of it, was people were trying to find the points within the space. So on the scroll challenge, we had scans of this ancient scroll, but it was actual pixel values. So one of the challenges that people were trying to solve was basically, how do you find that manifold? Because you have to like trace it within 3D space, and then once you find this, then you can do this same like unrolling process. But the difficulty was actually going from the dense pixel values down to like what is following the sheet of paper. So it's related, but the main challenge wasn't on the like actual unrolling of the manifold. It was finding the manifold itself.
Yeah. And then just as a side note, people, have continued to work on it. And it turns out that unrolling is actually very easy when the sheets are separate. The problem they had is that when the scrolls got charred and carbonized, there's places where adjacent sheets fused together and possibly got damaged. And so you can't actually separate them. But in the regions where they are, when you look at the X-ray, you can actually just see light, dark, and you can see the gap between each of the sheets. So in the better preserved parts, it actually was trivial to unroll them. The problem was that most scrolls are mangled enough that they have many non-trivial regions.
Yeah, so I pulled up, they have this page where they specifically say, they're like, this is a manifold, and they're trying to do some unwrapping of this, but the difficulty is actually like, we have this noisy scan and we're trying to find this squiggle line within it. If we have that squiggle line, then the manifold unrolling problem is easy, but when you just have an image, it's very difficult to do. You have something like this where it's very difficult to actually trace through. Yeah, go ahead.
And like most of the examples, it seems like we're dealing with Euclidean space, but then I'm wondering, do these algorithms, do they translate to like polar or parabolic or hyperbolic spaces?
It's very common for people to switch to cosine similarity and various other metrics when we start going into higher and higher dimensional space, because of these phenomena that I was plotting here, basically saying like, this is our Euclidean understanding where like at 3D it functions in a certain way, and when we go to 100D it doesn't really operate in the same way. So I would say cosine similarity, cosine distance is where most people typically go. But there are like a bunch of different metrics for how do you define points as close or far when you start going into this higher dimensional space.
Yeah, and I didn't see this in the chapter, but if you recall, in one of the first few weeks, I mentioned that it was talking about a certain algorithm in it, and the word distance appeared. And so the instant you see the word distance appear in the definition of any algorithm, it means that scaling is important. Okay. So if you had, I don't know, height of people in millimeters, and you had, their weight or whatever, and so you have one number that's like, up in the hundreds of thousands, and the other number that's like, between 0 and 10. When you talk about distance, the number that's really big, that's in the hundreds of thousands, is always going to dominate variance, is always going to dominate distance or whatever. So if you're going to do any of these techniques, you have to make sure your data is scaled. To your question, hypothetically, if you thought you had some insight into the data, you don't have to scale it in the obvious naive way. You could do something non-Euclidean, like, so the Euclidean thing would just be, hey, have them all be between 0 and 1, or variance 1. But if you really thought you knew something special about your data, you could scale them in a non-linear way in order to give the model a better sense of distance. Does that make sense?
So we're at the end of the chapter. I want to talk about a couple things that weren't covered by the book, though. So we talked about PCA. This is a plot that's showing side by side PCA, t-SNE, and UMAP. And so t-SNE for a period was very, very popular for showing, I have some data, I want to reduce it down to 2 or 3 dimensions, and it functions more like this LLE, where it cares about the local relationships of the points, and then it makes these nice plots for you where the points cluster together nicely, and you can say, oh, look at this group. Oh, that group all seems related in some way. And so you can go in and you can interpret it in some way. So for a brief period, t-SNE, everyone was making these plots and everyone was looking at them and going, oh, look at my data, make some little 3D interactive plot that you can scope through. And then after a little bit, UMAP really took over. People preferred this. It was faster to do to fit it on your data, and they liked the way that it visualized their data even more. So back in the day, this blog doesn't function anymore, but back in the day, Distill was like very high quality visualizations and explorations of all of the latest stuff. So they had this very interesting interactive view of t-SNE. So this is something where you can try it on different patterns of data and see how it groups it up for you. So it's very interesting how it chooses to do these dimensionality reductions. One of the things that they really highlight in this write-up, though, is you have certain choices of hyperparameters. So like I was talking about before, you can have trade-offs between how local are you looking, how global are you looking, how many steps are you taking in order to push these points around. And so if you look at, this is probably small, but you can see this is the original data, and then you can say fit it with a perplexity of 2, and it will run this whole simulation for us. And it's slowly gathering things up. And say if I set it with a perplexity of 30, then it just like crushes down to these tiny little balls. So there's a lot of interesting things with t-SNE. I'm personally not the biggest fan of it anymore because I think a lot of people kind of misread its purpose. I'm not a fan of t-SNE that much anymore. It is a very interesting technique to visualize your data, but I think people read into it a little bit too much, because what they're showing in this blog is I set my hyperparameters in different ways and I get totally different results. And so what people typically do is they say, run this 5 times with different parameters and then find the one that I like that comes to the conclusion that I was already thinking. And then they say, oh, t-SNE is great. But in reality, it will just, you can torture it to get whatever pattern out that you really want. So it's useful as a visualization tool, but you can't really read too much into its results. It's nice to kind of cluster your things up and look at what it says, but it can be misleading.
Yeah, I'll be even stronger than Ryan. One of the weird things about the t-SNE algorithm is that it it has this assumption that things that far away sort of fall into different classes. Okay. And so basically, it's really easy with t-SNE. If you have data that's just all bunched, you can actually create t-SNE charts that show lots of different small separate regions. Okay. So to the point, like what Ryan was saying about like torturing it. So if you have this hypothesis that there are three different kinds of blah blah organism and you have this data and the data does not support your hypothesis, you absolutely can find t-SNE parameters that will give you three clumps, three weird looking clumps. And that's a pretty terrible property to have. So it doesn't mean you can never use it, but like, yeah, it's really dangerous. And since UMAP, which I think you're looking at now, UMAP is actually faster than t-SNE. So I feel like there's really no reason not to use this newer algorithm instead.
This is a visualization I've been showing for many years now. I actually am a big fan of this. So this is a set of 10,000 words, and they've created embeddings out of these. So this is supposed to capture some understanding of this vocabulary, basically. And then it was trained in 300 dimensions or 100 dimensions, depending on which one you're looking at. Or maybe this one's 200 dimensions. But you can take it from 200 dimensions, reduce it down to 3 dimensions, and then you can visualize it like this. And so now this is this little interactive plot that you can go around on, and then we can dig into little clusters. So like, here's this little ball here, and it's saying pregnant, married, daughters, sister, wife, son, uncle. So it is useful for you can look around this, and these little clumps are probably telling you boxing stadium, tournaments, championships. It is showing you some relationship that is interesting. There was some 200 dimensional vector that represented something, and you can crush it down to 3D, and you can actually get some insight out of it. But I wouldn't read too much into this, because this is reducing the dimensionality a lot. And if I ran this is t-SNE again. If I run this with different perplexity, I can end up with totally different groupings. And so instead of having the, like, we saw a little like family bubble, it could then split to gender bubble. So it's man, son, all of that stuff together, and then woman, daughter, all of that in a totally different bucket. So you can come to completely different conclusions just by sliding this different ways. Yeah, so I think that's all I have. Anyone have any questions, anything they want to go into more details on? All right, cool. Thank you.
All right. Thanks, Ryan.